Hello, this is Mrs. Taylor, and I'm going to walk you through how to find the volume of a solid by cross sections. So the idea is that if I take some solid and I cut it up into really thin slices and find the area of each slice and add all those areas together, I'll get the volume of the solid. Think of like a stack of pennies. It makes a cylinder, but if I think of it as finding the area of a really, really thin penny and then adding up every single area of every single penny, um, then I can get the full volume. So the method that you will use to find the volume by cross sections is first, it's a good idea to sketch the solid and what a typical cross section looks like, because the shape of the cross section will dictate what type of area formula you're using. Once you've done that, you find the formula for area. So if it's a circle, it's pi r squared. If it's a square, it's s squared, and so on. Once you have gotten your formula for area, um, and I'm jumping ahead, in addition to determining what area formula to use, you've got to put it in the context of your problem. So what you're going to get is a base that's defined by functions. And so you've got to combine those functions in your area formula all into one. And this will make more sense once you see an example. So after you do that, you find the limits of integration. So that's where your solid begins and ends on your coordinate plane. And then after you do that, you integrate to find the volume. So again, this list may seem a little abstract right now, but we'll look at an example and hopefully it'll make more sense. So in this example, we have a solid that lies between the planes perpendicular to the x-axis at x equals 1 and x equals -1 and x equals 1. The cross sections perpendicular to the x-axis between these planes run from the semicircle y equals negative square root of 1 minus x squared to the semicircle y equals square root of 1 minus x squared. And so sketching some of these solids will help. A solid lies between the planes perpendicular to the x-axis. So what that means is that we've taken a solid and we have basically set it on a coordinate plane. And I'm going to slice it perpendicular to that plane. So in our sketch, these circles that are drawn, they're perpendicular to our coordinate plane. And so our cross sections are circles, so our area formula we're going to use is A equals pi r squared. And so I at least have my first step and second step, well, my first step done because I have my sketch. My second step, I'm halfway done because I know which area formula to use. But in order for me to use the algebra to do this, I need to somehow write my area in terms of these two functions, or use one of the functions depending on what information I need. So the idea is that if I'm finding the area of this circle, this slice right here, in order to find the area of the slice, I need to have the radius, right? Because area of a circle is pi r squared. So I have to find a way to define the area of this circle in terms of this graph. So if I start at the x-axis and I travel up to the edge of this cross section, which is my radius, the distance I just traveled is between the x-axis and this top curve, which is the top semicircle. So if you think about it, my radius is actually just y equals the square root of 1 minus x squared, because that's the distance. And the reason why we put it in the context of a function is because each cross section is going to have a different radius, but it will always be whatever your x value is plugged into this equation. And so I can rewrite my area formula here in terms of the function by writing a equals pi, and instead of r, now I can write the function square root of 1 minus x squared squared. And then, of course, if I simplify, squaring a square root, they cancel. And so my area formula is much simpler now because it's just pi times 1 minus x squared. Sorry for the sloppy handwriting. And so now I've completed step 2. I have got my area formula, and it is in terms of the function. And so all I have to do to finish is find my limits of integration, which they gave me. They told me that the solid's traveling from -1 to +1, and then integrate. So I'm integrating from -1 to +1, my area formula. And keep in mind that pi is just a constant. So when I integrate, I can just write it out front as a constant, just like we would any number. And then the integral of 1 is x, and the integral of x squared is x cubed over 3. Again, I'm sorry for this handwriting. It is bad. And then I would evaluate from -1 to 1. And so I'd have pi again times, that would be 1 minus 1/3 minus, and remember you're subtracting all of this with -1 plugged in. So put parentheses there just to remind yourself. And if I plug in -1, I get -1, and then -1 squared, or excuse me, this is cubed, so minus -1 would become positive 1/3. And the nice thing about this being a free response problem is I don't actually have to evaluate that. I can just leave it as the value, what I have there all plugged in. So I can circle this as my final answer and move on. Remember, anytime you can just leave it unsimplified, you should, because if I try to simplify this, I could make an error and lose all my points, whereas if I just left it like this, I'd get all my points. So that would be the, not area, but volume of that solid lying in that plane.